As we do this example, it's very similar to the example that we just looked at. However, notice that now our index is starting at 0 instead of starting at 1. Okay, so let's see how this plays out. We still have the same definitions, but I want to show how to apply those definitions in this situation. So, of course, the first thing we're going to do is we're going to look at our terms. Now, for our terms, right, the terms of our series. So these are terms of the series. Now, where do we get the terms of the series? The terms of the series are right out in front, right? So this gives me the nth term of my series. So let's look at this. So this should be pretty easy because the formula for the nth term is going to be 1 over 2 to the n. So that just means that a naught is going to be, well, so that's just 1 over 2 to the 0, right? So that gives me 1, and then 1 over 2 to the 1, so I get 1/2. 1 over 2 squared, right? You see what I'm doing? Because that's the formula is a sub n is 1 over 2 to the n. So I go ahead and I get 1/8 is the third term, 1/16 is the fourth term, yada, yada, yada. Now let's look over at these partial sums. So the first thing is terms of the series. Second is the terms of your sequence of partial sums. Now, the general formula for sequence of partial sums, Sn, the nth partial sum, is the sum of the first n terms, right? But now notice, because our terms are starting at n equals 0, we have to adjust our definition. So here, Sn starts counting at a sub naught, or a sub 0. So S naught, our first partial sum, is just going to be a naught, which is 1. Our second partial sum, which is S1, is going to be a naught plus a1, which is 1 plus 1/2. See, I'm just adding 1 plus 1/2, and then I'm going to get, that's going to give me 3 over 2. What about our third term? So we'll have S2 is a naught plus a1 plus a2. So I get 1 plus 1/2 plus 1/4, and that's going to be 7 over 4. Now, what about S3? If you notice, actually, to go from S2 to S3, I don't need to really add up all of these terms again. I could just instead take S2 plus A3, because this part right here is S2. So that's a neat little formula to recognize that Sn is equal to Sn minus 1 plus An. So we can define Sn recursively as well. Okay, so when I add it all up, when I add up, however I do my adding, I should get 15 over 8. Now S4, so I have 15 over 8 plus 1 over 16, and that gives me, let's see here, over 16, should be 31. Okay. Now, do we see a pattern? Do we see a pattern? Because we need to come up with a formula for Sn, right? We need to come up for a formula for Sn. So the question is, do we see a pattern? Let's highlight what we have so far. So we've got 1, 3 over 2, 7 over 4, 15 over 8, 31 over 6. What is the pattern? The denominators are all powers of 2. So in the denominator, we'll have 2 to the n. And the numerator, do you see that is 32 minus 1? 16 minus 1. 8 minus 1. 4 minus 1. And this we can write it as 1 over 1. So that is 2 minus 1. So it's a power of 2 minus 1. So this will be 2 to the n minus 1. And you'll notice that this formula is very, very similar to the formula that we had for Sn back when we were working with 9 over 10 to the n. Remember, the formula for Sn was 10 to the n minus 1 over 10 to the n. This example of 9 over 10 to the n, the series, and the series of 1 over 2 to the n are what are called geometric series. And remember, we'll have a special test for geometric series. Remember, we said we'll have a geometric series test. The reason why we can have a geometric series test is because the formula for the partial sums is easy to compute, right? So we said geometric series here, and then we're able to actually compute the sum because the formula for that partial sum is, we always know what the formula will be. So the limit of the partial sum. So we figured out that we've got a formula for our nth partial sum, which is 2 to the n minus 1 over 2 to the n. So the limit of the partial sum. So I need the limit as n goes to infinity of Sn. Limit as n goes to infinity, 2 to the n minus 1 over 2 to the n. I'm going to do that same old trick where I divide. I guess I should be using the big one here. Where I'm going to divide, or take this and multiply by 1 over 2 to the n, and my denominator, 1 over 2 to the n. So I'm going to get the limit, n goes to infinity, 1 minus 1 over 2 to the n over 1. This is going to go to 0, so my limit is going to be equal to 1. So in conclusion, the sum of 1 over 2 to the n starts at 0 to infinity, is the same as the sum 9 over 10 to the n equals 1 to infinity. So where you start, right, whether you're starting at 1 or 0, impacts what the sum is. Okay, so what we've done in this example again is we've determined whether the series converges or diverges. The series converges, and it converges to 1. And we've done this by looking at the sequence of partial sums. So our method was to investigate the sequence of partial sums. And as we said before, and you can kind of get an idea, investigating the sequence of partial sums can be time consuming, right? So if we have some tests that are quicker, we want to be able to use those tests, right? So each time that if we encounter a geometric series, we don't want to use, investigate the sequence of partial sums if there's a quick formula we can use, right? So if we can handle all cases of geometric series at once, that's a time saver. So that's the motivation for having different tests, right? Sometimes, however, as we'll see with this example right here, you'll have a telescoping series, and here you have to look at the sequence of partial sums in order to determine if it converges or if it diverges and what that limit is. So sometimes you can't help it. You've got to use the method of investigating sequence of partial sums. When you can, though, you want to use you want to use a test, a convergence test. So we'll learn about all of that in the upcoming weeks.